uh, augmented reality architecture. Here you can see the augmented reality system architecture diagram here. Uh, a process of combining or augmenting video or photographic displays by overlaying the images with useful computer generated data. The earliest applications of augmented reality were almost certainly the heads-up displays HUDs used in military airplanes and tanks, in which instrument panel type information is projected into the same cockpit canopy or viewfinder through which a crew member sees the external surroundings. Faster computer processors have made it feasible to combine such data displays with real-time video. Among the earliest and most prominent examples of this type of augmented reality, as first shown on the Fox Broadcasting Company's network in the mid 1990s, were the yellow first down stripes superimposed on television images of American gridiron football fields and the virtual flight paths added to help television viewers track the path of hockey pucks and golf balls. Now we are focusing on real world, the existing state of things as opposed to one that is imaginary, simulated, or theoretical. Here you can see a wet pavement after the rain. As an example, we can consider this real world object, your dog. Now we are focusing on capture real world. The background of AR applications is the real world done by cameras. Here you can see an example here. Here you can see architecture of an example capture session in Apple development. Configure input devices, output media, preview views, and basic settings before capturing photos or video. Here an AV capture session is the basis for all media capture in iOS and macOS. It manages your app's exclusive access to the OS capture infrastructure and capture devices, as well as the flow of data from input devices and to media outputs. How you configure connections between inputs and outputs defines the capabilities of your capture session. For example, this diagram shows a capture session that can capture both photos and movies and provide a camera preview using the iPhone's back camera and microphone. Now we are considering connects inputs and outputs to the session. All capture sessions need at least one capture input and capture output. Capture inputs, AV capture input subclasses are media sources, typically recording devices like cameras or microphones built into an iOS device or Mac. Capture outputs, AV capture output subclasses use data provided by capture inputs to produce media like images and movie files. To use a camera for a video input to capture photos or movies, select an appropriate AV capture device, create a corresponding AV capture device input, then add it to the session. Note iOS offers several other ways to select a camera device. Then add outputs for the kinds of media you plan to capture. From the camera you have selected. For example, to enable capturing photos, add AV capture photo output to the session. A session can have multiple inputs and outputs. For example, to record both video and audio in a movie, add inputs for both camera and microphone devices. To capture both photos and movies from the same camera, add both AV capture photo output and AV capture movie file output to your session. Important, call begin configuration method before changing a session's inputs or outputs, and call commit configuration method after making changes. Now we are considering display a camera preview. It is important to let the user see input from the camera before choosing to snap a photo or start a video recording. As in the viewfinder of traditional camera, you can provide such a preview by connecting an AV capture video preview layer to your capture session, which displays a live video feed from the camera whenever the session is running. AV Capture Video Preview layer is a core animation layer, so you can display and style it in your interface as you would any other CA layer subclass. The simplest way to add a preview layer to a UIKit app is to define a UI view subclass whose layer class is AV Capture Video Preview layer. Then to use the preview layer with capture session, set the layer's session property. Note, if your app supports multiple interface orientations, use the preview layer's connection to the capture session to set a video orientation matching that of your UI. Now we are considering run the capture session. After you have configured inputs, outputs, and previews, call start running method to let data flow from inputs to output. With some capture outputs, running the session is all you need to begin media capture. For example, if your session contains an AV capture video data output, you start delivering video frames as soon as session is running. With other capture outputs, you first start the session running, then use the capture output class itself to initiate capture. In a photography app, for example, running the session enables viewfind style preview, but you use AV capture photo output, capture photo with delegate method to snap a picture. Here you can see a AV capture device, back camera, and AV capture device input is connected to AV capture connections, and here you can see AV capture device microphone, and AV capture device input is connected to AV capture connection. AV capture connections are inside AV capture session, and here AV capture connection is connected to AV capture photo output, and here AV capture connections are connected to AV capture movie file output. And here AV capture connection is connected to AV capture video preview layer. Here you can see an example recording to MP4 video in Unity. When you are working with Unity Recorder, first install the Unity Recorder package, then launch the Unity Recorder, then configure record options and add a recorder. Then you can record to MP4 video, this one. You can also record to an image sequence. Here to record the video, so this is in Unity, and to record the video, add the movie recorder, set your recorder and movie option, then click start recording. The MP3 is the default movie format, but the open source web media format WebM is also an option. There are several wildcards available for the file name that will be replaced automatically when the movie is saved. For example, take in the file name will be replaced with the take number, which can be manually changed and increments automatically with each subsequent start of the Unity recorder. Unity will replace an existing recording with the same name without confirmation. So it's recommended to either give your movie a unique name or a dynamic wildcards such as take and time in the file name. By default, the path for your recording is relative to your project location, but Unity Recorder will store your recording anywhere you specify. By default, the Unity Recorder captures the game view, and the resolution can either match the game view window or be set to a present or custom value. Other options include another target camera or even a 360-degree view, which could be useful for capturing HDR environments for film and animation purposes. Audio capture is optional and enabled by default. Movie quality is set to high by default and can also be low or medium. As an example too, we can consider this one. Here m_video capture. This is from a class video capture. Records a video from the web camera directly to disk. Final video recording will be stored on the file system in the MP4 format. This class is in unity.vr.vsa.webcam, and here void start recording async string file name vr.wsa.webcam.video capture.only started recording video callback on started recording video callback. This method asynchronously records a video from the web camera to the file system. Parameters: file name, the name of the video to be recorded to, and on start recording video callback invoked as soon as the video recording begins. As an example 3, we can consider this code segment. Here you can see AV capture session. This class, the class AV capture session, an object that manages capture activity and coordinates the flow of data from input devices to capture outputs. So this is in Apple development environment, and here you can see the capture real world, run configuration, AR session configuration, and AR session has a subclass of subclass AV capture session, and as an output you can see AR frame, and AR camera is connected to AR frame here. Here you can see create the capture session here, and this is the rest of the code, video device here, and as an exception example, we can consider this Unity engine.xr.vsa.webcam.video capture stop recording async triggers and exception game assembly.dll video capture underscore stop recording video to disk underscore internal underscore M22843626669 video capture underscore T31910606632 asterisk underscore this comma etc. As an error example, we can consider this error occurred in Unity 5.6.4. Operation is not valid due to the current state of the object system.link.enumerable.first resolution. Enumerable one source. Now we are focusing on world tracking. Track the device's position and orientation in physical space. When the real world changes, such as moving the camera, it is necessary to track the position and angle change information of the current camera relative to the initial time in order to render the position and angle of the virtual world relative to the real world in real time. Here you can see 6DOF tracking maintains an AR illusion regardless of device rotation or movement. Here the 6 degree of freedom, here 3 rotation axis, roll, pitch and yaw, and 3 translation axis, movement in X, Y and Z. So here you can see a device rotation and Here you can see device position. Here you can see architecture of the AR kit. AR kit is the framework Apple introduced in WWDC 2017 for iOS AR development. The AR session configuration, AR frame, and AR camera are the main classes in ARKit API and can be divided into world tracking, virtual world, and capture real world, scene understanding, rendering, 5 different categories. In this figure, AR session is the core of the entire AR system, which implements the world tracking and scene understanding and other important functions. And here the world tracking is used to provide effective information for the combination of real world and virtual world, so that we can see more realistic virtual world in the real world. Here you can see AR session configuration. Run configuration is connected to AR session. CM motion manager is connected to AR session. AV capture session is connected to AR session. AR session is connected to AR frame, and output is passed from AR session to AR frame. AR camera is connected to AR frame, and AR frame is connected to ARS CN view, ARS K view, or custom view. Real world information is passed from AR frame to ARS CN view, ARS K view, or custom view. SCN scene or virtual objects are connected to AR SCN view, AR SK view, or custom view. As an example, we can consider this class AR world tracking configuration, and a configuration that tracks the position of a device in relation to objects in the environment. This class in the language Shift in Apple development environment. AR world tracking configuration class tracks the device's movement in 6 degrees of freedom. The 3 rotation axis, roll, pitch, and yaw, and 3 translation axis movement x, y, and z. This kind of tracking can create immersive AR experiences. A virtual object can appear to stay in the same place relative to the real world, even as the user tilt the device to look above or below. the object or moves the device around to see the object's sides and back. As an example, you can consider this NS undefined key exception. If not overridden, raises an NS undefined key of exception in set value for undefined key NS object NS string in NR world tracking configuration class in ARKit in .NET. Now we are focusing on scene understanding. In order to make the virtual world and the real world more realistic, it needs a certain degree of understanding of the real world, such as plane recognition. Here you can see a image engineering framework, and an image in a general sense is all types of media that can be understood visually by humans, such as video, animation, a still image, graphics, and so on. For these images, we as human beings gather information about the real world. Many techniques for understanding these images to acquire more information have been developed, and applications have been brought to existence. These techniques can be categorized under a 3-layer generic framework. So-called image engineering. As can be seen in this figure, these layers are image processing low layer, image analysis, middle layer, and image understanding, high layer. Image segmentation, as it is one of the most important steps in the task of image analysis, due to its due to its effect on the other steps in the framework. Segmentation has a significant effect on the accuracy of the object representation and feature measurement steps. Here you can see 3 layers: low layer, middle layer, and high layer. Here image understanding interacts with image analysis. Image analysis interacts with image processing. Image processing interacts with image understanding. Image analysis, image in is connected to image segmentation. Image segmentation is connected to object representation, and object representation is connected to feature measurement. Feature measurement is connected to image out. Here you can see the diagram that illustrate shows example of 2 application interfacing with scene understanding runtime. On the left hand side is the diagram of mixed reality runtime, which is always on and running in its own process. This runtime is responsible for performing device tracking, spatial mapping, and other operations that scene understanding uses to understand and reason about the world around you. On the right hand side of the diagram, we show two theoretical applications that make use of scene understanding. First application interfaces with MRTK, which uses the scene understanding SDK internally. The second app computes and uses two separate scene instances. All three scenes in this diagram generate distinct instances of the scenes. Driver is in tracking global state that is shared between applications and scenes. Applications and the scene object in one scene aren't found in another. Scene understanding does provide a mechanism to track over time, but this is done using the SDK. Tracking code is already running in the SDK in your app's process. Here you can see scene understanding runtime is in mixed reality runtime. Scene understanding runtime interacts with scenes, and here scene and MRKT is in the application process, and scene interacts with MRTK, and here two scenes are in the application process. So this is about scene understanding SDK with Unity. As an example, we can consider this one, initialization C# in scene understanding SDK. In initialization, the first step to working with scene understanding is for your application to gain reference to scene objects. This can be done in one of the two ways. A scene can either be computed by the driver, or an existing scene that has computed in the past can be deserialized. The latter was useful for working with scene understanding during development, where applications and experiences can be prototyped quickly without a mixed reality device. Here we will compute a new scene that's routed around the mixed reality headset and has a 10 meter radius. Here you can see create query settings for scene update. Here you can see a request that scene updates quads, and a request that the scene updates watertight mesh data, and here do not explicitly turn off quad interfaces, and here request static version of spatial mapping mesh, and here request the finest LOD of static spatial mapping mesh. Yep. And here initialize a new scene. As an example 2, we can consider this one, scene object enumeration in C# in scene understanding SDK. Now your application will be looking at and interacting with scene objects. This is done by accessing the scene objects property. As example 3, we can consider this using scene understanding in the Unity editor, and after installing MRTK feature tool, as example 4, using scene understanding in Unity editor, how to obtain a scene understanding scan for use in the editor. Step 1, clone the mixed reality toolkit from GIT hub. Step 2, open the project with Unity 2019.4.x. Step 3, install the scene understanding package using the MRTK feature tool. Step 4, open the scene understanding sample scene. Here it's in asset for /MRTK /example /experimental /scene understanding /scenes. Build the project with the scene as default scene 0 and deploy to HoloLens as usual. As an exception example, we can consider COM exception. COM exception when getting the result of xenobserver.compute async. As an example, as an error example, we can consider this error code occurred in when getting the result of xenobserver.compute async. This is my minus 21470248891. Now we are focusing on rendering real and virtual world. Rendering or image synthesis is the process of generating a photorealistic or non-photorealistic image from a 2D or 3D model by means of a computer program. The resulting image is referred to as the render. Multiple models can be defined in a scene file containing objects in a strictly defined language or data structure. The scene file contains geometry, viewpoint, texture, lighting, and shading information describing the virtual scene. The data contained in the scene file is then passed to a rendering program to be processed and output to a digital image or raster graphics image file. The term rendering is analogous to the concept of an artist's impression of a scene. The term rendering is also used to describe the process of calculating effects in a video editing program to produce the final video output. Here you can see a variety of rendering techniques applied to a single 3D scene here. Here we can, as an example, we can consider class renderer. General functionality for all renderers. A renderer is what makes an object appear on the screen. Use this class to access the renderer of any object, mesh, or particle system. Renderers can be disabled to make object invisible, and the materials can be accessed and modified through them. This class is implemented in unityengine.core module. As an example 2, the Unity single pass stereo rendering. To enable this feature, open the player settings menu, edit project settings, then select player category, then navigate to the XR settings panel. Ensure the virtual reality supported checkbox is ticked and select the single pass option from the stereo rendering method drop down here. Single pass stereo rendering is a feature for PC and PlayStation 4 based VR applications. It renders both left and right eye images and at the same time into one packed renderer texture that is twice the width of a single eye texture. Unity renders the scene twice using 2 draw calls for each game object that has a renderer component. However, it only iterates through the scene graph once when rendering for both the left and right eyes. During single pass stereo rendering, both eyes share the work required by culling and shadow computation. There are also fewer graphics command state change switches because the GPU renders each game object in a ping-pong fashion, alternates rendering of objects between eyes. Example 3. Following example demonstrate what you need to change in your fragment shader code to support single pass stereo rendering property. Single pass stereo rendering property unity stereo screen space UV adjust UV SB. If unity unity underscore single underscore pass underscore stereo is defined, this returns the result of applying the scale and bias in the SB to the texture coordinate in UV. Otherwise, this returns the texture coordinate unmodified. Use this to apply a per eye scale and biased only when a single pass stereo rendering mode. Uh, as an error example, we can consider this. The left eye is rendering incorrect light values, etc. in complex scenes involving multiple shaders. Here this occurred in Unity 5.0.0p2 in mobile SDK 0.4.3.1, Exynos Gear VR Android 5.0.1 Lollipop, Android ETC 2 OpenGL ES 3.0 Forced using the default mobile SDK project settings. Now we are focusing on augmented reality world. Augmented reality is an interactive experience of a real world environment where the objects that reside in the real world are enhanced by computer generated perceptual information, sometimes across multiple sensory modalities including visual, auditory, haptic, somatosensory and olfactory. AR can be defined as a system that incorporates three basic features: a combination of real and virtual worlds, real-time interaction, and accurate 3D registration of virtual and real objects. The overlaid sensory information can be constructive, that is, additive to the natural environment, or destructive, that is, masking of natural environment. This experience is seamlessly interwoven with the physical world such that it is perceived as an immersive aspect of the real environment. In this way, augmented reality alters one's ongoing perception of a real world environment, whereas virtual reality completely replaces the user's real world environment with a simulated one. Augmented reality is related to two largely synonymous terms, mixed reality and computer mediated reality. Here you can see Pokemon Go. Here you can see Niantic mapping the world. Now we are focusing on display, that which displays. Here you can see augmented reality systems standard design. The first augmented reality system, ARS, were usually designed with basis on three main blocks, as it is illustrated in this figure. The infrastructure tracker unit, processing unit, and visual unit. The infrastructure tracker was responsible for collecting data from the real world, sending them to the processing unit, which mixed the virtual contents with the real content uh, and send the result to the video out module of visual unit. Some designs used a video in to acquire required data for the infrastructure tracker unit. The visual unit can be classified in two types of systems depending on the followed visualization technology. One, video see-through. It uses a head-mounted display HMD that employs a video mixing and display the merged images on a closed view HMD. Two, optical see-through. It uses a HMD that employs optical combiners to merge the images with an open view HMD. HMDs are currently the dominant display technology in the AR field. However, they lack in several aspects such as ergonomics, high prices, and relatively low mobility due to their sizes and connectivity features. An additional problem involving HMD is the interaction with the real environment. Which places visual interactive zones to the user, making the collision with these zones hard due to the difficulty in to interact with multiple points in different depths. Alternative approaches to develop ARS involve the use of monitors and tablets. Monitors are used as an option for indirect view since the user does not look directly into the mixed world. Tablets are used in direct view since the user points the camera to the scene and looks directly into the mixed world. Both approaches still have difficulties in getting collision. To make easy the collision actions, here you can see real world visual data is connected to video in. Visual unit has video in and video out, and it's captured video out, and infrastructure tracker unit, you can see that unit here. Real world data from sensors are connected to infrastructure tracker unit, and infrastructure tracker unit is connected to processing unit. Positioning and orientation data are passed from infrastructure tracker unit to processing unit. Processing unit mix the realities, and virtual contents are passed to processing unit. Processing unit is connected to video out. Mixed realities are passed from processing unit to video out, and video in is connected to processing unit. Captured video for computer vision and image processing are passed from video into processing unit, and video out is connected to video out with mixed world. Here you can see a sample augmented reality scenario including 3 virtual screens. This illustration shows for virtual TVs or computer displays with high-end display glasses. This would provide a real alternative to large HD displays, combining low cost, high power consumption, high resolution, and perfect 3D rendering, overcoming almost all limitations of physical screens. And this with glasses not heavier, potentially even lighter than the current shutter glasses. In this example, we have decorated walls with dark rectangles, freeing space for insertion of visual display screens. This way we need no masking capabilities within the display glasses. The individual rectangles may be accent with block codes in infrared colors, for example, or with relatively dark image, a dark furniture surface, or a simple roll-up curtain. Using natural images for orientation is state of art. Meanwhile, an image could be subtracted from the virtual video in order to make it disappear. The different layouts of rectangles serves for their identification and for assigning them different video streams. Video streams can be provided by several real source devices, TV receivers, computers, media players, and for example, transmitted to the user's hardware via VLAN. It may be even possible to omit the PID. In this case, the orientation camera could also send its raw images to the source devices and leave them the computing of orientation and coordinate transforms. The crucial point in this example is a sufficiently good registration of virtual images to the real world. So distant objects, we can fortunately assume a collimated display model translating the glasses displays coordinates directly into angles related to the display. You can see the angles here in this illustration. What we get is non-changing linear relation between image of a position camera fixed to the glasses and projected image of the display glasses displays. Once the camera has located the corners of one of the rectangles, this gives us the exact position where to place the corners of a video display window in the glasses displays. All that remain is a simple projective transform of camera pixel to display pixel coordinates. This works well for large distances to displays. Usually the usual 2 to 3 from a TV should behave like infinity. For closer distances, it can be adapted to a certain degree by applying relatively simple corrections. Here you can see glasses coordinates here, and this is the virtual display image. These are real displays, and orientation camera is here, and orientation data is coming here, and these are the black area for virtual screen with optional infrared block code, and other virtual screen areas are here, and media player is here, and this is the rendered video, and smartphone or PID is here. As an example, we can consider augmented reality glasses. AR smart glasses are wearable computer capable glasses that add extra information, ideally 3D images and information such as animations and videos, to the user's real world scenes by overlaying the computer generated or digital information on the user's real world. Example 2, sample with Unreal glasses developed in Unity. Notice that the plus new vector 3 0 plus 0 1 0.125f0 has been added to make our cube that is tall 0.25 to sit perfectly on the marker. The bool nr kernel dot nr input dot get button down control button this returns true if the button was pressed down this frame. As an error example, we can consider this Unreal cannot run correctly here in Unity SDK 1.7.0 and Unreal SDK, and w/Unreal and etc. here. Now we are focusing on virtual world. Interacting with object model of the virtual world to increase the interest of the AR application. A virtual world, also called a virtual space, is a computer simulated environment which may be populated by many users who can create a personal avatar and simultaneously and independently explore the virtual world, participate in its activities, and communicate with others. These avatars can be textual, graphical representations, or live video avatars with auditory and touch sensations. Virtual worlds are closely related to mirror worlds. Here you can see augmented reality virtual reality world Pokemon Go. As an example, we can consider AR object placement with Unity. Add an object main and then add an object. The main camera is Z underscore REG underscore stereo. And the screen, if it's still running, right click the hierarchy and click 3D object, then cube to add the cube to the scene, and move the cube's position to 0, 0.5, 2, 0, 0.5 and 2. Set the cube's scale to 0.5, 0.5 and 0.5. Position the Z at table height and start the scene. You should now see the cube floating above the floor. If there's something other than floor under the cube, move the cube and or the Z until it's above the floor. Here you can see ARCore SDK for Unity sample app code for Android. The class game object, the base class for all entities in Unity space, as Unity scenes. Here, after planes are tracked, the update method handles user input for placing ARCore pawn objects on detected planes. When a user taps the screen, the frame raycast uses a raycast from tap position to detect whether the user tap a plane or oriented points. If the user taps a plane or surface oriented points, then AR core pawns object is instantiated at the trackable hit. If hit pause is used to create an anchor, the anchor keeps the AR game object in the same position related to the real world. When you no longer need an anchor, call Unity's game object destroy method. So the pawn is in the consistent orientation relative to the camera. When you no longer need an anchor, call Unity's game object destroy method on it. This signals ARCore to stop tracking the anchor. The camera position is used to adjust the ARCore's pawns transform so that the pawn is in a consistent orientation relative to the camera. Pawn's transform inherits the hits counter so that the pawn game object says where the user places it as the user moves their pawn around. And here you can see raycast against the location the player could touch to search for planes. Use hit pose and camera position use the hit pose and camera pose to check if hit test is from the back of the plane. If it is, no need to create the anchor. So this is else part, and here instantiate prefab add the hit pose. Compensate for hit pose rotation facing away from raycast, that is camera. Create an anchor to allow AR core to track the hit points as understanding of the physical world evolved. Make game object a child of the anchor. As an exception example, we can consider this in Unity environment. Null reference exception. A null reference exception happens when you try to access a reference variable that isn't referencing any object. If a reference variable isn't referencing an object, then it will be treated as null. The runtime will tell you that you are trying to access an object when the variable is null by issuing a null reference exception. This is a null reference exception on transform of a game object in Unity. As an example, here null reference object reference not set to an instance of an object. Here end of my presentation. Thank you very much for watching it.